Hello everyone, in this video we'll be looking at section 9.8, which is power series. So in the previous section we looked at approximating functions by Taylor polynomials. Right, we took this really awkward function and we represented it by an approximation polynomial that was a polynomial, right? It was powers of x's being added up. And the higher degree of the approximating polynomial, the better the approximation was. Right? So now what we're basically going to do is we're going to combine that idea of a Taylor polynomial, that approximating polynomial, with the infinite series that we talked about before. Right? And so in this section and the next two sections, we will see that several important types of functions can be represented exactly by an infinite series called a power series. So unlike in the previous section where it was just approximation, in this section we'll be looking at polynomials that are infinite polynomials, so there'll be infinite powers of x's being added up, and they will be exactly equal to our functions, right? Not approximations, exactly equal to. Okay, so definition of a power series. If x is a variable, then a power series is an infinite series of the form, and it looks like the sum from n equals to 0 of a sub n x to the n. In other words, it's just powers of x being added up, right? And these a sub 1, a sub 0, a sub 1, a sub 2, those are my coefficients. And again, that's when it's centered at x equals to 0. And more generally, when it's centered at x equals to c, it's the same thing, except we have that x minus c, just like we did in the Taylor polynomial instance. All right, so the only difference between a regular series and a power series is that a power series has the variable x in it. Right? It's still adding up infinitely many terms like a regular series, but because it has that variable x in it, it's actually a function, and that's why it's called a power series. Okay, so with every power series, we have what's called a radius and interval of convergence. So that's subsection 2 here. So a power series in x can be viewed as a function of x, right? So this is my power series, and it has a variable in it, so it can be thought of as a function, and we use our function notation f of x. And so it can be viewed as a function of x, where the domain of that function f is the set of all x for which the power series converges, right? So remember, this is an infinite sum, so an infinite sum doesn't always converge, right? But when it does converge, those values, those x values where this function, where this series does converge, is called the domain. All right, so every power series converges at its center. Why? Well, because if its center is x equals to c, then f of c is equal to the series from n equals 0, a sub n of, we're plugging in c for x, so c minus c to the nth power. So what does that look like? That looks like a sub 0, 0 to the 0 power, plus a sub 1, 0 to the first power, plus a sub 2, 0 to the second power, and so on. And 0 to the 0 power is defined to be 1, so this just becomes a sub 0 plus 0 plus 0, and so on, so it just becomes a sub 0. And my function is equal to a value, right? And we said that a number is in the domain if the power series converges. At x equals c, this function converges because it equals to a sub 0, right? So it converges. So whatever x value that I'm centered on, we know that our power series always converges at that point. The next theorem below states that the domain of a power series can take three basic forms, right? It can either be a single point, which is the center, or it can be an interval centered around that center c, or it can be the entire real number line, right? Okay, so it's theorem 9.20, convergence of a power series. For a power series centered at c, precisely one of the following is true. The first one is that the power series converges only at x equals to c, right? We proved just above here that we know for sure at x equals to c it converges, and say that's the only point where that happens. So what does this look like thinking about a number line? This is my x values here. The value x equals to c here, and that's the only value that works. Right? So this is a single point. So that could be the only value that this power series converges at. The other thing that could happen is there exists a real number r greater than 0 such that the series converges absolutely for the absolute value of x minus c less than r and diverges for the absolute value of c greater than r. So what does that mean? Well, that means, remember, anytime we have absolute value of something minus something, that is telling us an interval, right? Because absolute value means plus or minus, right? So what this is basically saying is what we could have happen is we know at C we're good, right? And we also know that if I take this value, which is C minus R, and I take this value, which is C plus R, then I know that everybody in this interval converges, right? Again, this is the distance R, this is the distance R, right? When we think of this absolute value, that just means the distance between X and C. Is R, right? That's what it means to be absolute value, right? So the other way, what this is telling us is the other type of convergence we could have is some interval centered around C, right? So this is an interval. And then the third thing we could have happen is that the series converges absolutely for all X. Right, so again, at C, we know we're good. And then actually for every other value, we know we're good too. Right, so this is the whole real line. So for any power series, we know that it converges. We know that there are three basic three basic forms that the domain can take, right? Again, the domain is all the possible X values that are allowed. In this case, that's the X values that make this power series converge. And so the domain can either be a single point, an interval centered at C, or the whole real line. And so anytime we start talking about convergence of a power series, we start talking about this radius of convergence. Right, and so like looking at number 2 there, R would be the radius of convergence, right? So obviously in case number 2, when I have an interval, we see that that's just the interval, right? R is called the radius of convergence because it's like the radius of a circle, right? It's the distance from the center to the outside. However, in case 1 and 3, we also talk about the radius, but we think about it almost a little redundantly. So if the series converges only at X equals to Z, then the radius of convergence is R equal to 0, right? In other words, the radius there is no radius, right? It's just that single point. If the series converges for all X, then the radius of convergence is R equals infinity, right? In other words, that radius extends infinite distance from on the left and to the right of C. So the set of all values of X for which the power series converges is called the interval of convergence. So in order to determine the radius of convergence and the interval of convergence, we're going to use the ratio test. So remember, in general, the ratio test, what did the ratio test tell us? If a general series, not a power series, but if a series converges, or if it diverges, right? And so that's kind of the idea that we're going to use in this case for the power series. Because again, a power series is a super specific case of a series in general. Okay, so just as a side note here, let's go ahead and write out what the ratio test is, just so we're all on the same page here. So again, the ratio test, remember, what does it say? It says if the limit as n goes to infinity of a sub n plus 1 over a sub n is less than 1, then it converges, right? Then the series converges. If the limit as n goes to infinity of a sub n plus 1 over a sub n is greater than 1, then we know it diverges. Right? So that's kind of the idea we're going to use in this analysis of figuring out the radius convergence of a power series. Okay, so we've got this power series. Remember that, let's think about, first thing, what is the center of this? Remember, the center is the value that I'm subtracting from x, right? Remember, what did we say? The center here, when it's just x by itself, we know it's centered at 0. And when I have x minus something taken to a power, we know it's centered at c. So in this case, since it's just x, we know it's centered at x equals to 0. So just for fun here, let's show that indeed for x equals to 0, this series converges, right? We won't do this every time because we actually already proved that it's always going to converge, right? That's what we did here. But just for this specific case, let's show that. So if x equals to 0, right, the center, then f of 0, right, we're calling our series f of x. F of 0 is the sum from n equals 0 of n factorial 0, because 0 is what I'm plugging in for x, to the n. So what does that look like? That looks like 0 factorial, 0 to the 0 power, plus 1 factorial, so I'll need the parentheses there, 1 factorial, and then 0 to the 1, plus 2 factorial, 0 to the 2, and so on. So notice that this is 0, this is 0. Here, 0 factorial is defined as 1. That's how we define factorial starting out with. And 0 to the 0 power is defined at 1. So this whole guy is just going to be 1 plus 0, and so on. So it just equals to 1. Right? So indeed it converges for x equals to 0. Right? Because it equals some value. Okay, so now the idea is we got to find other values that it converges at. And again, the way we're going to do that is by looking at the ratio test. So let's say if x does not equal to 0, what we're going to do is we're going to let u sub n just be equal to what I'm adding up, right? What each term is. So n factorial x to the n. Then we're going to form the ratio test on u sub n. All right, so then the limit as n goes to infinity of u sub n plus 1 over u sub n is equal to what? And remember, whatever we get for this answer, we know that if it's less than 1, it converges. If it's greater than 1, then it diverges. Right? Okay, so let's plug everybody in. So n plus 1 means we plug in n plus 1 into u, so I end up getting n plus 1 factorial x to the n plus 1 over top of n factorial x to the n. We'll need to do some algebra as per usual. So remember, in the last video we talked about what is n plus 1 factorial. N plus 1 factorial is, again, every number before n being multiplied to get before n plus 1 being multiplied together. And we talked about how n plus 1 is really can be written as n factorial times n plus 1 factorial. Oh, sorry, not n plus 1 factorial, just n plus 1. So n plus 1 times n, try that again. N factorial times n plus 1 is how we can rewrite n plus 1 factorial. And then x to the n plus 1 can be written as x to the n times x, right? Because remember, if I'm multiplying two things, then I add their exponents. And if I add n and then x to the first power, I end up getting n plus 1, and we're back where we started. And then I get n factorial over x to the n. So I see some things are going to cancel. N factorial cancels, x to the n factorial cancels, and I'm left with the limit as n goes to infinity of n plus 1 times x and the absolute value. Notice here I'm not losing the absolute value because n, we know it's a little bit redundant to have the absolute values around that, the n plus 1, because n is always positive, right? It's the indice that I'm adding up, but the x, we don't know if it's positive or negative, right? The x values, that's what we're trying to figure out. So now what I can do is I can factor out the absolute value of x, right? So I guess for this instance, let's go ahead, since this is the first time we're doing it, let's rewrite this. This is really n plus 1, because I can lose the absolute value around n plus 1. But actually, let's just keep there again, just so we realize what's going on, times the absolute value of x. Right? That's just properties of absolute value. I can always like distribute the absolute value. So again, now the x is independent of n, the limit, so I can pull that out front. It's like a constant. And then I take the limit as n goes to infinity of n plus 1, because n plus 1, again, is always positive, so I don't have to have the absolute values. And now what do I get? I get x times infinity, right? When I plug in, when I evaluate that limit, it's infinity, so I know I get infinity. So what have we shown? Remember, the idea was we're looking at the ratio test, right? If this guy is less than 1, then it converges. If it's greater than 1, then it diverges. Infinity is obviously greater than 1, right? So what does this mean? This means that by the ratio test, the series always diverges, regardless of what value I put in for x here, right? Right? So what does that mean? That means for x such that the absolute value of x is greater than 0. Why do I say that? Well, if x is exactly equal to 0, it's the only thing. Remember, x, if the absolute value of x is equal to 0, then that means x is equal to 0. Any other value of x means that the absolute value of x is greater than 0, right? Because even if it's negative 0.001, the absolute value of that's still going to be greater than 1, and even if it's positive 0.0008, we know that the absolute value is 0.008, again, still greater than 1, right? So just saying for all values other than right here, I said for x specifically not equal to 1, and then I said everybody other than 1 equals to diverges. So this is just a fancy way of saying everybody but x equals to 0. So for x greater than or for the absolute value of x greater than 0, in other words, everybody but x, the series diverges. Right? So what does this mean? That means that the only guy that works is the center, right? Remember, if the only guy that works is the center, is our radius of convergence is 0. Right? So what we figure out here is that sorry, I have to put it up here, I'm running out of room. My radius of convergence, I guess we can put it down here, is r equal to 0, right? Because there's no other values other than r equals, other than x equals to 0. Okay, so let's look at one more here in this video. So let's look at this guy. So once again, I could show that for x equals to 2, that this is going to converge, right? Because x equals to 2 is where it's centered at. But we won't waste our time proving that because we know that that's true in general. So again, this one is centered at x equals to 2, right? In this case, in the case above, what did we end up looking like? We ended up looking like I just had this value 0 here, and 0 was the only guy that worked, right? That was why I had a radius equal to 0. Okay, so this guy we're centered at x equals to 2. So now we're going to do the exact same trick that we did above. We're going to say, okay, so for everybody else, for x not equal to 2, because 2 is our center, we are going to let u sub n be equal to my terms being added up. So 3 times x minus 2 to the n. And then we're going to perform the ratio test on u sub n. Right? So we're going to say, okay, the limit as n goes to infinity of u sub n plus 1 over u sub n is equal to, now I plug in our values. So I end up getting 3 times x minus 2 to the n plus 1 power over 3x minus 2 to the n power. Oops. So remember, anytime I have n plus 1, that just means that I'll rewrite it this time, but then we'll start getting used to not rewriting it to save ourselves a little bit of time. This can really be written as x minus 2 to the n times x minus 2, right? Because again, if I multiply those, I add their coefficients, so it gives me n plus 1, and then I get 3 over x minus 2 to the n. So we can see I get things to cancel. So I end up getting the limit as n goes to infinity of x minus 2. Right? And notice this is the limit as n goes to infinity. There are no n's inside of there, right? So it's just a constant, and remember the limit of a constant is just whatever that constant is. So I get x minus 2 there. So you're like, what? How does this work? Well, remember, the whole idea is we're using the ratio test, right? So the ratio test says this limit converges if this guy is less than 1, right? So by the ratio test, the power series converges if whatever the limit is, which we said the limit was x minus 2, the absolute value of x minus 2 is less than 1, and it diverges if the absolute value of x minus 2 is greater than 1. Right? So remember, looking back up to our cases, remember if I end up getting that the absolute value of x minus my center is less than some value, then that value that it's less than is going to be my radius, right? So what does this mean? This means that my radius of convergence is r equals to 1. Right? So just to say what we've got going on here, remember, where are we centered at? We're centered at 2, right? And then we have a radius of 1, so I go here to 3 and I go here to 1, and I know that I work for 2 and I work for everybody in this interval, right? This is adding 1 to 2 and subtracting 1 to 2, right? So my interval of convergence, which the question didn't really ask for, is going to be 1 to 3. And now later in the book, they go into detail about figuring out whether I put brackets or parentheses, whether it's a closed interval or open interval. But for our case in this course, we're not going to worry about whether it's open or closed at the endpoints, right? We're just going to consider looking at the open intervals. Right? In other words, that's why we're really only concerned about what the radius of convergence is for these questions. Right? That's just what I asked. What's the radius of convergence? But I think it's an important analysis to look at it. Okay, so that's all for this video. We'll pick up in the next video with example C there.